It's my pleasure to have the opportunity to speak to you. I don't normally speak to journalists in large groups, so this is new to me. And so one of the issues that the public has been very concerned about as a result of this oil spill is, the relative safety of the seafood and the seafood that's commercially harvested and sold, and also recreational fishing. And so what I want to go over briefly today is how the heck are these decisions made, these judgments made about relative levels of safety of seafood. And I'll start just by introducing the overall health risk assessment process, getting in a little bit into risk management, which is kind of what you do with the data that's developed there. And there's an example of Louisiana Seafood Safety Monitoring Report, which I think was distributed to you ahead of time in your packets. And I'll go through an example calculation of how they develop one of these levels of concern, and then discuss the limitations of this overall process. So the health risk assessment process is the one that's used primarily. Has been kind of codified by what's called the Little Red Book, which was put out by the National Academy of Sciences in 1983. It's a multi-step process that, some of these steps happen concurrently. But you start out with the hazard identification. Basically, you try to figure out, do we have something bad here that we need to worry about? And then you get into the dose response assessment. That's the toxicology angle. You figure out, okay, if it's bad, how bad can this stuff be? And there's a lot of different ways to study that. When you're dealing with, when you're thinking about human health, usually you can't study humans for toxicological reasons. There are, the pharmaceutical industry does extensive testing for clinical trials with drugs and so forth. But most of our knowledge about exposures to typical environmental pollutants most of our human knowledge comes from occupational exposure studies, because there you have, large groups of people who are exposed to relatively high concentrations of pollutants all the time. And so, but that's kind of the limits of our ability to get human data. So most of it is done in cell lines, in animals, and different assays. And you try to, and you usually have to expose them to relatively high concentrations of pollutants in order to see something. And then the challenge is to extrapolate that back to a concentration level that's relevant to human exposure. Yes, question in the back?
So these are all fairly short-term exposures to
this study, the animal studies?
acute effects? So short-term experiments with acute effects is what you mostly can look at?
No, it's a range. You have short-term acute studies, and then you have probably the longest studies is the classical cancer bioassay using rats. It's about a 2-year study. So it's a range. If you have just acute lethality studies that can be done in a relatively short amount of time, and those are the initial studies to figure out what's the appropriate dose to use in the larger study. Because you basically want to choose a dose that's high enough that you're going to see an effect, but it's not too high to kill all your test animals.
So I'm curious about how you could see effects on reproductive systems and in life cycles and
That's whole other branch of toxicology where you do multi-generational studies and in rats and mice, and there's a whole gamut of types of toxicological studies that can be done. But data from these studies is used to try to, again, like I said, extrapolate down to levels of concern to human population. Because if you just expose, if you're interested, let's say, in a cancer risk of 1 in a million, 1 in 100,000, well, and you only have 200 rats in your study, and you've got a couple different exposure groups, there's only 50 per exposure group. So you're going to have to extrapolate. There's a huge gap there in terms of what you know and what you're trying to extrapolate to. Not to mention the fact that you're studying rats and not humans. So you have, it's very challenging to do this. But then the next step of the process is the exposure assessment, trying to figure out what people are exposed to. This example today I'll go over is with seafood, but this overall process is used to make judgments about pollution in any environment, in air, in water, in soil, in other foods, and so this overall framework fits with all of those. And then finally, the characterization of the overall risk. The risk management aspect is the part of the process where you take the science, if you will, and it's not a completely separate process from the risk assessment, health risk assessment process. But let's incorporate political pressure, economic decisions. I mean, the Soviet Union was known as having some of the strictest environmental regulations on the planet, but they were meaningless because they were just on paper, they weren't enforced. So you can't just make up a number and say, whoa, this is we're regulating to this level. Well, but if you don't do it, then it's just kind of it's just an exercise in futility. So the process for health risk assessment of chemical contaminants in seafood involves, the hazard identification and dose response process for each chemical. And like I said, this process is it can be used in any environmental media. But you've got the part of the process I'm going to focus on today isn't so much the toxicology side, it's going to be on the exposure assessment side. So exposure to seafood includes getting the data, taking samples of seafood out in the field, getting laboratory analysis on what's there, and then making a judgment of what are the consumption rates, how much seafood do people eat. This is the example report that's put out weekly now from the Department of Health and Hospitals, this Louisiana Seafood Safety Surveillance Report. And this is the one, there's a March 31st one last I checked, maybe there's another one even now. And, but this is the one, the basis for which I'm going to show an example calculation about how they come up with these numbers, how the heck do we do that. And the one thing I wanted to just, it can be kind of intimidating maybe to those of you who aren't familiar with dealing with these chemical concentration units. I mean, lots of acronyms, lots of fancy units. So in the seafood chemical concentration data is in, they say milligram per kilogram. So that's just, it's a weight measurement. So it's a ratio of the weight of a certain chemical contaminant to the weight of the overall sample. Another type of chemical concentration unit that you may see used is a part per million or a part per billion. And the way I like to explain it, it's just a fancy kind of percentage is all it is. There's no units to it. 1 part per million is the same as 0.00001%. And so if you have 1% concentration, that'd be the same as 10,000 parts per million. So we use units like parts per million and parts per million so that we can function by using whole numbers. Whole numbers are a little bit easier to deal with than having like so many decimal places out there. So that's one of the reasons we use that. So this is a table from that report. It's captured from that. It's slightly blurry. I think you should be able to see it. So this is seafood sampling results as of March 14th. And it gives the sample, so they began sampling on April 30th, 2010, and continued to this day. And they break the categories of samples from, sample oysters, shrimp, crab, and finfish. And this gives the total number of samples that are collected. Now, the way the sampling is being done, it's not that they sampled 754 oysters. There's 754 kind of batches of oysters that were analyzed. And then, and the same goes on for shrimp, crab, and finfish. And then you have this concept of detection limits, of was the chemical detected at all in the samples, or was it not detected? So you can see with oysters, in large proportion of the samples they did detect some of these compounds that are listed on the slide. Then they report above the level of concern, 0, 0, 0, 0, 0. Okay, it's all good.
Are you just looking for hydrocarbons or dispersants as well?
I think the first report that has any dispersant testing data is the March 28th report, which just came out. This is the March 14th report. That brings a point I didn't mention before is so they selected a record. You can't analyze for like the whatever 800 compounds that NOAA apparently is testing in the water over time. That's just simply unworkable. So you try to kind of find a representative group of compounds that are important toxicologically and that they think would be related to the oil spill. And these polyaromatic hydrocarbons listed on the slide here are the panel of compounds that was selected to study over time. And then this gives the concentration range. So it goes from non-detected to 0.057 milligram per kilogram for oysters and so forth. So, but what I'm going to discuss here as we go on is looking at these comparison values for polyaromatic hydrocarbon compounds. This is the panel of compounds they've been studying. Some are carcinogens, some are thought to be carcinogens, some are not. They're not carcinogens. Anthracene is the one example calculation I'm going to go over here. So they give the level of concern for anthracene, and they group shrimp and crab together, is 1,846 milligrams per kilogram. And there's different levels of concern for different groups of seafood. So oysters have a different level, but finfish have 490. But the ratio of these, the shrimp, the crab number to the oyster number, all the way down the table is the same, because that's using the assumption of the consumption assumption, or the seafood consumption rate, is what's driving the difference between those numbers. Yes, but
I was just curious, the levels of concern, how is that calculated? Was that again, how much seafood someone's eating? If you're looking at a population.
That's a great question, and that's actually what the rest of the presentation is going to be about.
No, that's all right.
Good segment.
Okay, is the concern death, or is the concern just health problems?
No, well, the concern is twofold. For carcinogens, the concern, and I think I have in this next slide, I'll go to, as part of answering your question here, the concern, you can broadly categorize, carcinogens and non-carcinogens, the cancer health effects and non-cancer health effects. And you can have, for the same compound, you can focus on, for a carcinogen, you can look at the non-cancer effects of that compound too. You have to choose a risk level. When you're developing these levels of concern, when you're developing, let's say you're developing a regulation for air pollution, you have to choose, well, what's an acceptable level of risk that you're going to allow people to be, and this is an excess risk, so what you're already exposed to. And so the acceptable level of risk that was chosen by the FDA and NOAA for their assessment is the level of 1 excess tumor in 100,000 people exposed over a lifetime to, so let's say they were eating fish, shellfish at this level, over a lifetime of exposure, you would predict from the risk assessment modeling that 1 out of 100,000 would have a tumor. And that you'd bump up the cancer rate by 1 in 100,000. Now, for non-cancer health effects, there's a lot of different health endpoints. You can say, liver toxicity, kidney toxicity, and so forth. And for that, there's a process by which, and they use the EPA process of developing what's called a reference dose. And a reference dose is a level of exposure, again, over time, that at that level, you wouldn't expect to see any adverse health effect over time. So it's cancer and non-cancer. The cancer calculations is a little bit more tricky, and I originally was going to go over an example of that, but they used a special approach of toxic equivalency between different polyaromatic hydrocarbons, and it got a little bit too muddy. So I said, all right, I'm going to do non-cancer. And then, so this level of concern, then you take the toxicology data to determine that level, and then finally the exposure assessment. So this is the simple calculation, some basic arithmetic here. You've got a level of concern. It's equal to the reference dose times the body weight times the conversion factor and the consumption rate. The reference dose is, again, this level of daily human exposure at which you wouldn't expect to see any health impact over time. The body weight that they chose to use was 80 kilograms. So this is just a single point estimate, and this is a population-based approach. You're not really trying to assess an individual's risk. You're looking at the overall population. So they use the CDC Health Statistics Report. In the old days, we used to use 70 kilograms. So now, with 80 kilograms is enough. And there's a conversion factor to make the numbers all match up. But then finally, there's the seafood consumption rate. And for shrimp and crab, oysters and pinfish, there's a different rate. And I've got a table here that shows that a little bit better. And they used the NHANES data, the National Health Examination Nutrition Survey, which is a long-term study that government's been doing, kind of following people's health over time, to get, and they ask people questions about what do you eat, how often do you eat it, and they use these data to come up with these meal sizes. The FDA selected to use the 90 percentile number, so a high fish consumer. But the meal sizes, I think, are kind of low in terms. For example, I had a shrimp po' boy for dinner last night. Oops. And I'm pretty sure that I had more than 3.2 ounces of shrimp.
When we start talking about fish populations, human populations, we're talking about long-term exposures beyond 3 months. We have the local and systemic kinds of exposures as well, depending on what types of things are occurring. Benzene, for example, the volatile fraction of crude oil, is one of the constituents that we're most concerned about because it is a known carcinogen. But its time frame in terms of actual exposure from an oil spill, its residence time sitting on the surface of the Gulf of Mexico is anywhere between an hour and a half to 2 hours max as a result of loss to the environment. So we have all these kinds of inputs that occur as we look at what happens when something goes into a body of water. We have this air-water interface and this water-sediment interface. So it's a little bit different in that you have to realize that what's going on in the atmosphere moving into the water column, there's one set of dynamics and one possible type of exposure mechanism at work. And then when you get beyond that point where you're going to start dealing with this water-sediment interface and what's on the bottom, other things happen. So a chemical coming into the environment, whether it be benzene, whether it be any other constituent in crude oil, whether it be a pesticide, and I assure you here in Louisiana, I know around the LSU campus in my lab, within a 25-mile radius, we have every known toxicant to name. Okay? Radioactive, you name it. And so in any given environment, it's going to either have something dissolve, it's going to precipitate, it's going to fall out of solution, and then of course it can resuspend and come right back up. A very classic thing, in fact, one of the little quiet things that no one's really talking about yet about this oil spill, but we have lots of areas where we know we have oil sitting, you know, between sandbars and the coastal barrier island areas, and the Coast Guard is attempting to deal with how do we physically get all of this out of there. And that's a resuspension event. So what we don't think has been an exposure mechanism in the actual process of remediating it, we're reintroducing an exposure mechanism. So it could resuspend. We sometimes break this up into what we call the non-biological aspects of things moving into the aquatic environment and the biological aspects. And so, for example, we can have a chemical spill and then boom, we have volatilization and it moves right back up into the atmosphere. In fact, here in Louisiana, the environmental movement really began in '77 when we had an 18-year-old kid back a truck up to a large pit and open up a valve and just dump hazardous waste into this open pit. That was a chemical reaction, that was a volatile discharge, and that young man was dead in 30 seconds. Ooh. And so, I mean, these things happen. One of the big issues that's going on in Japan is this volatilization, non-volatilization. That is the wrong button. You gotta remember that. I know a lot of grad students would say, hey, where's that button? Then you have light playing a role here as well. You know, one of the issues about this spill initially was we have this air-water interface that's very nebulous. You know, if you really looked at it, it goes from water to a little air to a little less water air to more air than water, and then we're in air. In that really dynamic matrix, you have all kinds of chemical reactions going on. Analytically, for example, in the New Orleans area, in Baton Rouge and in Houston, we pull an air sample and we run it through our databases. We can only identify about 25% of all the chemicals we're seeing. So that means 75% of the stuff we're breathing, we don't even have a name for it yet. Okay? So we have this photolytic cooking matrix that's going on as well. We have hydrologists, things can dissolve, and then on the other side of the fence, the biological part, we have bioaccumulation, biodegradation, biotransformation, and we have the things that we're more familiar with as things move up through birds, through mammals, and to man. Well, when we're looking at a mammalian system, us, for example, we worry about these 3 routes of exposure. Inhaled air is 1, the gastrointestinal tract is 2, and of course the skin. People tend to forget that there's a dermal exposure. But that mechanism also occurs in the marine environment. You know, I tell my students that this is the biggie, and this is the one we worry about. You know, if you take a child in a kindergarten class and you say, well, we're worried about that child drinking water, a kindergarten kid will drink about 2, maybe 3 liters of water a day. But that same child will breathe in 20,000 liters of air. So we have different routes of exposure and how things occur. This inhalation route is a biggie. Gastrointestinal is also one. You notice we have the blood and the lymph system. We have all of this resulting in things being disposed and parked in different locations, and of course the dermal as well. In the aquatic and the marine environment, everything we're dealing with is swimming in what we're worried about. So we have inhalation, we have fish breathing in what's in the water. We also have the fact that they're swimming in it, and shrimp and oysters, of course, are filtering it. And then, of course, we have this traditional, what we call trophic level of exposure, or, if you will, consumption. So we have this really complicated mix where we have different species accumulating different things at different rates. The key point made earlier this morning about how some of these constituents that make up this very complicated food chain, one of the things we don't know yet about this spill is, will some of these players be missing next year? But we do know what is actually moving into each of these fish species, and we tend to focus on what's there, what's the edible portion, you know, what is the constituents of concern. We all know what we mean by dose. We know that if there's a substance and you take it, there's a given quantity, and we use something like an LD50. That's what we do. That's pharmacology. But in aquatic toxicology, there's also an LC50, lethal concentration, where seafood, you know, where fish and so forth are swimming through this water. And then there's also an EC50, where there's an effective concentration, where we can see that certain things that happen. We mentioned earlier about mercury, and mercury still is the best model for me to kind of walk you through what's going on here. There's an excellent paper that was published over 30 years ago by Boudot and Rebeb out of Bordeaux University and Marseille. The French are ahead of us in so many areas vis-a-vis metal toxicity. Why? Because they have a lot of it, and their real estate is a lot shorter than ours. You know, the old dilution is the solution to pollution. Well, after a while, the Mediterranean can only be diluting so much. And so the French, at least, are very sensitive to what's going on. Boudot and Rebeb did this really neat little experiment where they looked at the methylated form, or the organic form of mercury, and the inorganic form of mercury, and they looked at it just going in the water column at different temperatures, at different pHs, and they took 2 pathways. One is direct, you know, swimming in it, and the other one is trophic, feeding. So they either allow their species to swim in it or feed in it. And they took something very simple like an algal species, chlorella, our workhorse from an engineering perspective, Daphnia, and moving on up to rainbow trout in terms of the food chain. And some of the key things about this paper that you need to be aware of is, for example, how quickly both the methylated and the non-methylated forms moved into the water column, quickly was absorbed by chlorella. Time frames for equivalent here in Louisiana for an algal species to absorb all of this metal is about 2 hours. So if you had a mercury spill in South Louisiana, before you could respond to it, mercury is already moved out of the water column, is already into the algal community, and is now food at the primary productivity level to start moving up the food chain. Different rates for different organics, but again, the beauty of this little paper is they then went in and looked at, as you went up the food chain, where did it all go? For example, here's the inorganic form of mercury building up in the gills, and the organic form of mercury in the gills. And if you go to the gills down to the blood, you'll see that the blood levels are going up as well as a result of this route. And if you then look at the liver chemistry and you look at the spleen is a good place to look at fish in terms of where things are going, you can track how these mechanisms are occurring. The intestinal tract, you notice these numbers, that y-axis is not the same as the y-axis here. So there's a barrier here, there's a barrier here, but this barrier is a little bit more effective in keeping things out, if you will, versus breathing it in. But then it all combined, whether it's coming that way or if it's coming that way, it still gets into the blood. And the thing that we worry about is this one right here, because this is mercury accumulation in the edible portion. Finally, here's the brain up here, and this is fish, but it applies to children. There's another blood-brain barrier. There's another barrier that these toxicants move through. And notice that even though it's less in concentrations compared to some of these others, it's over time, this is a 30-day window, it's continually going up. So, I mean, this is a piece of work that was done years ago, but it's still, oh, there's the wrong button again. It's a still great model. So here's all the models they came up with for liver, brain, gill, muscle, intestine, kidney, spleen, and blood. And you can pick one of these and you can see it goes up very quickly over 10 days and kind of tapers off, or it stays kind of linearly and keeps going on and on and on. So when you look at muscle, for example, it's curve number 2 or curve number 3, depending on whether it's the inorganic form or the organic form. So again, really, really nice piece of work. One of the other things that Boudot and Rebev did in their work, and we tend to forget this from a toxicological perspective, is they also looked at how long is it going to take to decontaminate. How long is it going to take for the species to eliminate this? All of you women in here have more DDT in your body than us guys, as a result of a product that was used up through 1979. Your grandchildren will be the first children in this country not to have DDT in mother's milk or placental transfer. So we're talking about 50 or 60 years to decontaminate from something that's been banned in this country since the early 80s. So this decontamination process is important. So here's Boudot and Rebev's paper again, showing how quickly you stop the exposure, bam, the gills drop like a brick. As a result of that, the intestinal tract isn't taking as much in, and the blood is, of course, not transporting this material. You know, one of the earlier things we did in toxicology is we pulled blood samples from fish. Well, if you chose the wrong time and the wrong exposure mechanism, you didn't see anything. Or let's look at the gill material. That's a valid thing to be doing. But again, if you miss that window, you're not seeing anything here because you're in the decontamination mode. So that's 250 days. Notice, though, what's happening to that mercury in the edible portion. It's still going up. And also the brain is still going up from another 30 or 40 days. And it kind of plateaus after 250. But you notice it doesn't go down. It doesn't end up where you want it. And so we have all of these really neat curves and models that are still very applicable, depending on what you're going to look at. For example, we have some things like the gills, where the concentration goes up, but it comes right back down. But we have something like muscle, where the concentration goes up, and during the decontamination process, it continues to go up. We don't know the implications of this spill long term because we don't have the data yet on the decontamination part. So there are reversible effects. There are things that can happen in terms of no lasting impact. And then there are these irreversible things where there are permanent effects, and we don't exactly know about that. a couple of questions were asked about hypersensitivity and hyposensitivity. And again, most people worry about allergic reactions when you're talking about seafood. Very few people have talked about like benzoate-pyrene, which to me is the toxicant of concern in seafood. Some other things you want to worry about, of course, this irreversible to reversible mechanism in terms of an effect, whether you're going to have a lethal effect or you're going to have a sublethal effect. And as we just talked about, this level of concern issue is really this decision tree we're making between the margin of safety from one side of the fence to the other. There are these things called phase 1 and phase 2 reactions that I just wanted to mention, because you're not allowed to give a toxicology talk without saying phase 1 and phase 2. Basically, we're talking about phase 1. Your body is attempting to make something less toxic and try and modify the structure so that you can eliminate it, i.e. make it more water soluble. And that's you, that's shrimp, that's crabs, that's oysters, that's seabirds. Going through this first step of trying to change something from a very lipophilic or oil-soluble material to something a little bit more water-soluble. And then we go, and here's some examples of phase 1 reactions. And so in the human body, we have the cyclone P450 system. And I always ask these biochem majors, where did the 450 come from? And they all kind of look at each other. And it's because it's the wavelength at which this enzyme was first identified on a spectrophotometer, 450 nanometers. They thought it meant something very specific, like a gene sequence and so forth. So it's just old 450, and there's P448 and all of these others. Then we go to these phase 2 reactions where we're trying to eliminate it from the body and hence get it eliminated through the kidneys and so forth. And the model that I use is you're taking something like a Volkswagen and you're attaching it to another model so it's now an 18-wheeler so your body can eliminate it. And that's what some of these phase 2 reactions are with these very complicated structures. When we're doing drug testing, we're not looking for the parent molecule. We're not looking for what went in. We're looking for the 18-wheeler coming out. And that's one of the things that the guys in the Tour de France haven't quite figured out yet. The laboratories are looking for 18-wheelers. Okay? So with that in mind, we have these phase 2 reactions, and these things are going on. So to summarize, we have a toxicant that can be detoxified and excreted from the body. We can have a toxicant that can have no effect, go right through unchanged, and there we are. Or we can have something that is metabolized, and usually in toxicology, certainly in aquatic tox, a lot of these metabolized materials, they're very active metabolites, and they usually do more harm than good. There's also something called a protoxicant, something that we don't normally think is toxic, but when we get into this transformation process, we end up with something a lot more toxic. And again, a good example of that historically has been something like toluene or phenol, some of the other constituents you find in gasoline. You know, it's not a good thing that you're breathing gasoline when you pump gas, because you're breathing benzene, of course, carcinogen, ethylbenzene, toluene, and xylene. While you're chewing or doing that whatever, and doing all these other things, you're actually dosing yourself. So you're giving yourself either a toxicant or protoxicant while you pump gas. And so you can have a very primary reaction where this toxicant hits something in the body and you end up with a modified receptor, and all these other things can happen. We don't have the data yet from this spill to understand all of the things that are happening. The first three speakers this morning hit on these things. That could be enzyme inhibition, some kind of cell membrane, some kind of disruption. Something happens that we don't initially see, or as we go through the next life cycle of those species, we see a toxic effect. We haven't really talked about behavior, but in aquatic toxicology, for example, we looked at fish swim differently. For example, fish love the smell of copper. Copper's toxic, but hey, this stuff smells great. And the behavior is they swim toward it. So they swim right into the toxin. We don't have a good handle about how well fish smell oil. We suspect that certain components, as it weathers, actually attracts fish, and other components in the more weathered phases do not. So we end up with all of these possible exposure mechanisms, and I have to jump ahead a little bit. And I'll just skip endocrine disruption, because finally we end up with, as we said, this risk kind of calculation. Again, it's identifying the hazard, what is the dose, what is the exposure, in order to calculate risk. So paraclesis, this phrase, which was the dose of the mixture makes the poison, in my first slide should say it does, but differently for genetically different individuals and differently at different times during growth and development. Always mindful that lower doses may be more poisonous than higher doses. So you have to have a legal 21st century interpretation of poisons. And then just finally, I was just going to show you that if you look at some of the real data in some of these areas, it went too fast here. Okay, go in reverse. Let's see. Is this the reversal? No, it isn't. We already been talking about level of concern, and I was going to just point out to you that benzoate-pyrene, to me, is the constituent of concern, because we use benzoate-pyrene in remediation, in soil remediation, sand remediation, beach remediation, in terms of doing a risk calculation. When we clean up Superfund sites, when we clean up RCRA sites, I'm doing it time. The regulatory people convert everything into benzoate-pyrene equivalents, so they can have one number to look at, because they love that. I don't want to look at 98 different pHs and make a calculation. Let's convert everything to one benzoate-pyrene. And so I tend to be looking at the benzoate-pyrene. So this is the, and then this is the DOSS, that constituent and corrects it, that Food and Drug has been looking at. So here are the level of concerns for the dispersant. That's what the data looks like when you go on the website. So, you know, you got to get a magnifying glass. Here's some of the Century data. We haven't talked much about it, but you know, the big smell test issue. How do you smell seafood? You know, olfactory evaluations and so forth. Just wanted to show you that a lot of the seafood that Food and Drug is looking at moving into commercial applications, you know, literally passes the smell test, as you can see here. And then, again, just to show you for different data sets out in the Gulf of Mexico, actual field harvested. Here's brown shrimp. Level of concern is 132 parts per billion. The actual measurements across all of these sites have been about 0.5 parts per billion. Here again, for tuna and different fin fish, about 0.5, less than that. And the level of concern is 132. And then the surfactants, notice the numbers go from ppb to ppm here, right? And the level of concern is 500 parts per million. I haven't been able to get a handle on how they made that decision on the 500. And then in terms of actual different fish stocks, again in terms of tuna and so forth. So just to show you that in toxicology, we're not there yet. We do use something called toxic equivalence. The World Health uses it. We don't really have a good handle yet in this country on what we think is a toxic equivalent for all the things we're looking at in the oil. And again, the one that I look at is benzoate-pyrene. But we do have TCDDs and TEQs and so forth based on our benchmark toxicant, where we think everything in the world other than from botulism, the most toxic chemical is 2378 TCDD. And so World Health eventually will come up with better numbers for TEQs. And the way to look at whether the seafood is safe or not is when we finally have TEQ values, because now that is not just talking about selling seafood on the domestic and local market, but in terms of international commerce. So be looking for some of those numbers. This past week, for the first time, Japan came up with TEQ values for seaweed and fish, for iron, for iodine and cesium as a result of the spill. That was something they really didn't want to do, but they had no choice because food is being sold from Japan worldwide. And so they had to say, this is how toxic our seaweed is. This is how toxic our fish is. So as we look at the data from this spill over the next year or two, we'll come up with some TEQ values. And we'll come up with an answer. By the way, the book Blessing is coming up here on the bayou. And this is the other famous Cajun down here, other than me, of course. It's Mike Blanchard on the BP commercial. And thanks very much.